Correct. Okay, so thank you all for your faithfulness. So this is the last in the series, and actually, so
faithfulness and discrepancy.
Yeah, the last theme I want to discuss is about important local action. And yeah, basically, there is one last piece of math that I want to explain to you. So this is a theorem that I observed with Philip Wesolek. Will be here next week. And basically, it makes concrete what I already announced already. So let T be a locally finite tree. With more than two ends. And the automorphism group of T acts co-compactly. For example, a D regular tree. And H be a compactly generated locally compact group with whose own. So I want to say whose only amenable normal subgroup is the identity. And let gamma be a co-compact lattice. Okay, so what I want to say is that if gamma is irreducible, then we know that one way to say this is that the projection on top T of gamma is non-discrete, and the local action at every vertex of T is nilpotent, then the projection from gamma to H is not injective, and gamma is not residue finite. And I should, I need just a little bit more than nilpotent. I want really to say nilpotent and fixed point. Okay, so I remind you what I mean by the local action. You take an arbitrary vertex of your tree T, you look at the stabilizer of that vertex in gamma, you look at how it acts on the link of that vertex, and I want that the finite permutation group that I see acting is nilpotent and has no fixed point in the link. Okay? And so just to, to fix ideas, so what you should think of for the group H would be, for example, the automorphism group of another tree, T, the D regular tree with D at least 3. That's a very good example of a compactly generated group, blah, blah, blah. But you can also have for H a product of two or more groups of this form. Okay, and then examples of gamma to which this will apply. So a gamma, an example of a lattice gamma as in the theorem is gamma, the gamma 2, the group, the BMW group to which I referred to constantly in my previous lectures. So this was an irreducible lattice in a product of two trees, and on the first tree the local action, so it was vertex transitive and the local action was like D4 acting on 4 points. So it's a group of over 8, it's nilpotent, it was transitive, so certainly fixed point free. And there is another example. It's the wise lattice. I mentioned this example earlier, so this is a BMW group of all the 3, 2. So it's an irreducible lattice in out T6 cross out T4. Okay, and we mentioned earlier that, so Danny proved that this is irreducible by showing that the vertex stabilizer is inseparable. And we don't know that this is actually equivalent to saying that the lattice is irreducible. And then Danny, using this, considered the double of this lattice over the vertex stabilizer. This becomes an irreducible lattice in out T6 cross out T8. And then by construction, this is not reasonably finite. But actually, Danny's initial example, so it's already irreducible, and the local action here, it's S3 cross S3 on 6 points on the left-hand side. So that's the local action. I showed you yesterday how you compute local action. It's really easy once you have the presentation. And on this side, it's C2 cross C2 on 4 points. So this is, again, nilpotent fixed point free. So the theorem shows that this example also cannot be reasonably finite. Okay, so yeah, let me show you the tools. For the theorem. So the first one, I think it goes back essentially to the work of Fürstenberg. It's something that was alluded to by Adrien in his talk on Tuesday. So Fürstenberg showed kind of an abstract version of the Borel density theorem that applies to all locally compact groups. So Borel density theorem says that the lattice in a semi-simple group is Zariski dense. And from this, you deduce, for example, that the center of a lattice is contained in the center of the ambient group. Or the centralizer of a lattice is also contained because you centralize a Zariski dense group. So the centralizer of a lattice must be contained in the center of the ambient group. Okay. So although the Zariski topology does not exist for locally compact groups, you can still wonder about the consequences of the Borel density theorem. And so Fürstenberg proved essentially that. So let H be a compactly generated locally compact group. So I really copied these assumptions. So with no amenable normal subgroup of the Zangi identity, then for every co-compact lattice the normalizer in H of gamma modulo gamma is finite. I mean, it's actually a corollary of so that's the piece of information that we will use. But actually, so even without assuming H compactly generating or gamma co-compact, Fürstenberg proved that the centralizer in H of the lattice is trivial. Okay. And so that's the key result. And it implies this statement, why? So now assume that H is compactly generating and gamma co-compact. If, okay, then gamma is finitely generated. Okay. But then the automorphism group of gamma is countable. Okay. And so the normalizer in H of gamma, this is a closed subgroup of H. Okay, and so it, because the centralizer is trivial, so this will inject in the automorphism group of gamma by this. But this is countable, so you get a closed subgroup of a local compact group that's countable, and by Baer theorem, so that must be discrete. Okay? And so the normalizer is also remains a lattice, but then you have, so gamma is a lattice in a discrete group, so this index must be finite. That's how you finish. So gamma is a lattice in a discrete overgroup, so this overgroup must be a finite index. So that's one bit. The second one is again something, so for abstract lattices, so let gamma in G cross H a lattice in a product of a totally disconnected locally compact group G and a group H as before, so compactly generated with a trivial amenable radical. Okay. Let U in G be a compact open subgroup. Then if the normalizer in G of U over U is infinite, then the projection of gamma to H is not Okay, again, let me just illustrate this with a counterexample. So for G, you can take Z. H, you can take ZP, the p-adic integers, and gamma, the copy of Z diagonally embedding. Okay, then you indeed get a lattice. Okay, for U, so this G is discrete, so a good example of a compact open subgroup is the identity here. So this is infinite, it's the whole group G. So the only thing that's wrong in this example is that H is amenable. It does not have a trivial amenable radical. So so this proposition, it follows essentially from Fürstenberg theorem. So let me sketch the proof. So U is open. Therefore, the normalizer of U is open because any overgroup of an open subgroup is open. And so the intersection let's call it lambda, this intersection, when you intersect a lattice with an open subgroup, it's a lattice. Okay. But inside lambda, you have a smaller group, which is the intersection of lambda with this one. So this is also a lattice in U. Okay. But U is normalized by its normalizer, so what you see is that lambda U is normal in lambda. Okay. The index of lambda U in lambda, it must be infinite if this quotient is infinite. So lambda mod lambda U maps onto a finite index subgroup. This quotient, because lambda is a lattice inside this group. And on the other hand, so because U is compact, you can also project lambda U to H. Modding out the compact subgroup, it's a proper map. So lambda U maps onto a lattice of H. But then by Fürstenberg's theorem, the normalizer of a lattice here is a finite index overgroup. So when you project H to H lambda, this quotient is finite by Fürstenberg. Okay, so something was killed in the projection, which is what we get. Projection is not. It is that's the second tool. And finally, so there is the bit where the nilpotent local action plays a role. So now it's purely a result on groups acting on trees. Let's see the quantity. The group acting compactly with nilpotent local action at every vertex. Then there exists an edge such that the normalizer in G of this edge stabilizer is an infinite index overgroup of the edge stabilizer. Okay, so if you believe in this, and also in this proposition, so back to the theorem, we assume that gamma was a lattice in a group acting on a tree satisfying this. So the assumption here is satisfied. So we get a non-injective projection on the second actor, and I already explained you earlier why non-injective projection will give you non-residual finiteness of lattices. So, yeah. This is a rather geometric statement. So basically, I can explain that. So the lemma on nilpotent group that we use is the following. So if for any nilpotent group F, and for any H proper subgroup of F, the normalizer in F of H strictly contains H. That's a basic result of nilpotent group, so we can prove it easily. So a nilpotent group, by definition, it has if it's non-trivial, it has a non-trivial center, and the center normalizes everything. Every subgroup is normalized by the center. Okay. So if H does not contain the center, then the normalizer of H contains the product of H times the center, which is bigger by the assumption. So the only case remaining to check is when H contains the center of F, but then we pass to the quotient modulo the center, and we use induction on the nilpotency class. Okay, so that's really straightforward. So, but now if you think, what does it mean for nilpotent permutation groups, which is what we have in our setup? So if F acts is nilpotent and fixed point free, so what does this tell us? Then for any point, okay, Okay. I can look at H, the stabilizer of that point. The action is fixed point free, so I know that this is a proper subgroup of F. Okay. And now the lemma tells me that there is an element of F that normalizes H, but that's not containing H. So saying that it's not containing H, it's exactly saying that it moves the point I. So by the lemma, there exists J in F, such that Ji is different from I, but it normalizes H. Okay? So what you get is really the fact that in a nilpotent fixed point free permutation group, the fixator of one point always fixes at least one other point. That's what we have just shown. Okay. So, Fi fixes at least one point J. And that's essentially all we need. So now we consider G acting on the tree T with the action co-compact and so locally nilpotent fixed point free. Then pick an edge. Okay. So you look at the stabilizer of that edge. Okay. And now what can I say? So I know that the local action around this vertex is nilpotent fixed point free. So I can apply what I know. The stabilizer of one point inside this finite group fixes another point. So this means that the stabilizer of that edge fixes another edge. And same on the other side. And then I continue. So the conclusion is that the subtree fixed by the stabilizer of that edge is infinite. Okay. But then I use the fact that my action on the tree was co-compact. Use a co-compactness argument, and then I get an infinite. All the edges appearing on that fixed point set fall into finitely many G orbits, and then I have to use that to find a non-compact normalizer. And actually, there is a
Here you really need fixed point free, not only nilpotent local action.
Yeah, you need fixed point. Actually, you need just a little bit less. So if you had a global fixed point for the local action, if you had two or more global fixed points for the local action, you would be fine. So what you don't want is that at some point you arrive at a vertex and that this point is the unique fixed point of the local action at this vertex here. So, and actually you don't really need nilpotent. The only thing we use is the fact that every point stabilizer has more than one fixed point. That's the only thing we use. So that's the condition. Okay. Anyway, so I won't say more about this. Yeah. Indeed, Just, I want to, because I mentioned nilpotent local actions, so there is another global property of a group acting on a tree with nilpotent local action that's a bit even more straightforward to establish. So that's another proposition which I find so related to this. So let G act on the tree, B finitely geometric group acting without fixed points. If the local action at every vertex is nilpotent, then G virtually maps onto Z. And here I don't need fixed point free, and again I don't really need nilpotent, I need something else. So, so this is to say, here is another global algebraic property of the group G, namely to be virtually indicable, to map virtually onto Z, that you can recognize from the local action. So if you want an example of this would be G an amalgam. Okay, and I just assume that A modulo the normal closure of C in A and B modulo the normal closure of C in B are both finite nilpotent. Okay, then G modulo the normal closure of C in B is virtually indicable. So that could be, if you teach a class on Basler theory, that could be a homework project. So the only thing about about these nilpotent groups that I use, I don't really use the fact that it's nilpotent. The only thing I use is the fact that it's not the normal closure. This is the normal closure, but here I want to write the normal core. Okay, so this is the local action. In the action of G on the Basler tree, the local action of A around the link of the vertex fixed by A is this finite group. Okay. And yeah. Okay, and so the hint is that, so this quotient, it acts on the quotient of the tree by the group. And G acts transitively on the Basler tree of that. So this action will also be edge transitive. And then what you prove is that this quotient graph is actually a tree, and it's an unbounded tree. And then you will get a group acting actually properly because you divide it all in a normal closure or edge stabilizer, you get a group acting properly on an unbounded tree. So this is why it's actually virtually a free group. But this unbounded tree could be a line, so I cannot do better than virtually. Yeah, so let me now, basically, it's too late for me to start another, discussing another topic. I just want to finish by a few concluding remarks. So basically, yeah, all the technology that I presented and all the insights that Mark and Shara had to construct virtually simple lattices, so they provide us with examples. So we know by doing a sequence of manipulations, we know how to produce certain examples, but we also know that there is a profusion of examples of BMW groups, and most of them, only parts of the tools that I explained will apply. So, for example, if you remember what I explained yesterday, so we had the way to construct a virtually simple group was by starting with a small one, acting in a product of two small trees. And then we knew how to find such examples that are not reasonably finite, and then we had to embed this in a larger example. To make sure that this one is just infinite. And then because it contains the smaller one, it's both just infinite and reasonably finite. That's how we knew that it's actually virtually simple. But now if you think about this group, so it acts co-compactly in a product of two trees, but there is something very specific which is built in the construction, is the existence of a sub-product of two trees whose stabilizer acts co-compactly there. I mean, this is something very specific. The existence of a big subcomplex which is convex and periodic, that's something, I don't think that's the genuine case. And so, yeah, the kind of question that, there are many questions here, but questions suggested by all these findings of Mark and Shara include, for example, so what are the closures of projection of irreducible compact latitude in the product of two trees. So even if we fix the trees, we focus on lattices that act vertex transitively. Okay, we know that we'll have, for large trees we have many examples, and so what are the possible closures of lattices? It's something we understand poorly, and we know that some properties of the closure of the projections induce nice properties of the lattices, but there is no complete understanding whatsoever. It's really, so this requires, I think, especially if you are interested in just infinite lattices or virtually simple lattices, we need first to understand simple groups acting on trees. That's why I chose this title. And it's a subject in its own, but it's a subject for another lecture series. So I will stop here.
about questions. There is only one. So
Yeah, so if you want...
should they
Okay, one. Here is another. So let G just be an amalgam, okay, with locally finite. So with the locally finite amalgam. So fine. So under fine condition, on the local action, for G, you have normal subgroups, infinite normal subgroups of infinite inverse. Okay, so all the hereditarily just infinite lattices in products. So you can look at their action on one side, and the local action on one side is always doubly transitive. Locally, doubly transitive. So if the local action is too small, like a nilpotent group, then the group is always virtually indicable, so it has normal subgroups. And so if the local action is something between too transitive and nilpotent, it's not really clear what happens. And I'm willing to assume things on A, B, and C, because if G is a lattice in a product of two trees, I will know that A, B, C are free groups. Okay. So I think that Mark has a conjecture that if A, B, C are free groups and G is hereditarily just infinite, then the local action is too transitive. But that's no. And yeah, so we know that what's very important to realize here is that so you won't have an acylinical action. I mean, these A, B, C are, of course, infinite groups. So G is an indiscrete subgroup of the automorphism group of the tree. So the pointwise stabilizer of any ball is non-trivial. So it's really orthogonal to any kind of WPD condition. Or, yeah. So finding normal subgroups is we must develop specific tools. Are you happy with that second question?
You mentioned last time the case of 3 trees. Is there any sort of attempt or strategy that you think will be successful?
So there are two things to say. So the first thing is that all the theoretical results that I presented for product of two trees, they have analogs on the product of at least two. Okay. So but the problem is to find examples. So there is no exotic source of examples. At least if you want examples that are again just infinite or virtually simple. Okay. But actually, I think that it's actually related to understanding better a product of two. because I mean, if you have gamma the lattice in the product of three trees, okay, and then again, so each time you fix a vertex in one of them, this will give me a lattice in the product of the first two. Okay? And if my goal is to find something exotic, gamma virtually simple and so on, then I'll have to assume very strong irreducibility properties and something about the closure of the projection being simple and so on. So this will imply that all projections are injective, even though I'm not assuming that gamma is reducibly finite. But so the suitable irreducibility conditions will imply that gamma injects in each factor. But now think about the vertex stabilizer here. Vertex stabilizer in a locally finite tree, that's a reasonably finite group. Okay, and so what you get is, in particular, a reasonably finite exotic lattice in a product of two. You see? So even before starting, one way to exclude an exotic lattice in a product of three would be to show that an exotic lattice in a product of two cannot be reasonably finite. You see? But again, the kind of ways that we obtain specific non-reasonably finite examples, it does not tell us something on the general example. Yeah, this kind of argument was used in another setup for lattices in certain buildings that come from Catholique theory, where Nicolas Monod and I obtained, for some cases, results saying that any lattice in a product of two such buildings, if it's exotic, it's not reasonably finite, and therefore there cannot be a lattice in a product of three such. But it really exploits the specificity of these examples and the fact that although these buildings are exotic, they contain sub-buildings that are Bruyati's buildings, and then you can exploit that to obtain more information. But that kind of reasoning is absolutely not available for trees.
And there are a lot of arithmetic lattices in products of K trees.
Yes, I mean they are arithmetic, and you can also find lattices that are not just infinite and exotic. So this is also possible. But, virtually simple ones. That's the thing that we can do.
And this gamma 2, that was the first one for which you could prove that it was the first example of a virtually simple that was not residually finite.
No, gamma 2 was not the first of anything. It was just one more example of a non-residually finite. Its only good quality is it's in size. It's very concise. It's only 4 generated, 4 related. So, yeah.
But I always forget what you can. So there is something that you suspect that they are all not residually finite and that you cannot prove for an example.
Yeah, I mean that would be so. If you can show that, I don't know, for big trees, an irreducible lattice which is locally alternated, the local action is alternating on both sides. If you can show that this is actually enough for the lattice to be non-reasonably finite, then as a corollary, you prove that
Yeah.
there cannot be lattice in a product of 3 with locally alternating. It's time for the weekend to start.
Start out the questions.